So, so today we are going to discuss the concepts that are there in the week 11. I guess this is the last week for your maths one, and the week 10 and 11 are I can say is the most important part for your final quiz. So I guess not half, but I guess 30 to 35% of your final quiz paper are from graph theory. Almost 5 or 6 questions are directly from from the graph theory. So, like this is the most important portion for your final quiz that I can see. So it's better that you should have a command on graph theory. So week 11 will be discussing today. Uh, I guess I'll start with topological sorting. Then we'll see the longest path in a DAG or basic DAG, and then we'll go to calculate the shortest path from a single point, single vertices. Okay, like there are three algorithms: Dijkstra algorithm, Bellman-Ford, and Floyd. So three algorithms are there. So we'll try to cover up all these things in today's meeting. Okay, rest of the things are not that difficult. I guess the difficult portions and the important portions are the topological sorting and the longest path in the DAG. This is what I guess you should be knowing. Other than that, I guess the other parts are very simple. Even though if you are just going through the lectures, you'll be able to do it. Okay, so how many of you?
Good morning, sir.
Hey, good morning. How many of you have went through the lectures of week 10 and 11?
The week 10 is completed, and the week 11 is not.
Week 11 is left. Okay. So I guess what
Yes,
is the deadline for week 11?
I think the 12th or 13th December.
Okay. So yes. So okay, I'll just give you the brief idea about the 11th week today, because I guess the deadline is 12th or 13th and the quiz is on 26th, I guess.
Yes, sir.
24th.
24.
Yeah, so I'll just go through the 2 3 topics and maybe just try to go through that. And after that, maybe in the next session, whatever the remaining portions will be there, we'll do that. You're able to see my screen, right?
Yes, sir.
Yes, sir.
Visible.
Good morning, sir.
Hey, good morning. Good morning, everyone. So, okay, so let's, I'll just write it down. What are we going to discuss today? So, we'll try to cover up at least you are able, I guess, the topological sorting you have already done, right?
Yes, sir.
Yes.
In week 10.
Yeah. And then you have Dag. Okay, dag. So you would have read it.
Directed acyclic.
Correct. The longest path in dag. And then there is like the shortest path, or you can think of the transitive closure also. Shortest path in a weighted graph. And this can be three algorithms that you have to read. Dijkstra algorithm, the last part is MST. Okay, so these are the portion that you have to read it in week 11, I guess. And yeah, so we'll start with topological sorting, and then we'll try to wrap up uh, as much as we can. Can somebody tell me what is this topological sorting?
Sure, it's basically arranging the vertices of a given graph in order of their n degree.
Right. So basically, whatever the if you have been given a graph, we are trying to write some sequence, right? In some sequence, the vertices, whatever has been given to you, you are trying to write in a some sequence. And what is the relation in that sequence if you are wanting to write it in some sequence? Any sequence that you are writing, A, B, C, D, like there is a graph that has the vertices is A, B, C, D, E. If you are writing in this form, in the some sequence form, A, C, B, D, E, what does that mean? That you have to finish work A first and then you can do it C and then B and D. Or maybe there is a dependency of D on E, right? Or maybe there is a dependency of C or A. Okay. And the opposite case, like there is like if you have, okay, so first of all you are aware of what is directed graph, right? You are already aware of directed graph. What is directed graph? Can somebody say me what is directed graph?
Direction from one point to means one vertex to next another vertex.
So
Which
basically, the edges are not non-directional. Like they're not necessarily connected both ways.
Okay. So if I'm saying if you have a is this a directed one or a non-directed graph?
it is directed
Why it is directed?
because we have mentioned the direction of in the edge we have mentioned the direction of vertex.
Okay. Now tell me, is it a directed one or not?
Second one is directed.
Hmm? Both,
Directed.
both are
Both.
directed. See, you are already aware that this both are same, right?
Yes.
No, sir.
What?
No, sir.
How?
What is the meaning of this line and two-sided arrow?
Yeah, both are same, right? Basically, whenever you are writing A or both represent the same thing. Okay, but if you're writing something like this, that means B is dependent on A. Okay, whenever you're
Okay.
writing the adjacent the matrices, how do you write that? You're writing in such a way that you can reach B from A, correct? But you can't reach it A from B, right? If the arrow was like this means that you can reach some city A from B and you can reach B from A. Both are possible. That doesn't mean like if you can ask me is like how can somebody is going from A to B and he can't reach to A from B. It's like there is some flight from A to B, but there is no flight direct flight from B to A. Okay, this is what the this mean. In the similar way, this also represents the same thing that like even though there's no arrow been given, but it means the same thing that you can reach from there is some flight from A to B also and from B to A also. Okay, so if you have even a single directed graph with all the graph as bidirected, you can say that this is a directed graph. Okay, this is what I was trying to say. Is it clear to you, everyone? Is it clear? Are you able to hear me?
So,
Yes, sir.
Okay. So did you understand this?
so
Yes, sir.
Okay. Okay, tell me what is DAG then? Okay, so directed graph was pretty simple. I don't think so there is much to know about that. What is DAG then?
It's a directed graph without any cycles.
Yeah, the full form itself is like a directed cyclic graph. Okay, so acyclic means what?
Will not cycle.
So there are some properties of a DAG. Okay, so the first thing is it doesn't have any cycle. The second property is you are already aware of what is in degree or out degree of any graph. So every DAG basically has a vertices, has a vertex with in degree equals to 0. And the third is every Directed acyclic graph has a vertices without degree equals 0. Okay, these are some properties. Okay, so basically this means you have a directed graph. The first thing is what should be directed, and it should not consist of any cyclic graph in that. Okay, did you understand this? So if I am giving you two graph 0, 1, 2, 3, and 4. Now tell me this is a diag or not. The first one. The second one is tell me which of the two is a diag. So basically a diag is a graph. First you have to check it two things, right? It should be a directed graph, and then it should not consist of any cycle. Okay, which of the two doesn't? So you'll agree that both of them are directed graph or not? So the first one and the second one, both are directed graph.
First one is DAG. Yeah, both are directed gap, and first
Yeah,
one
both
is
are
a DAG,
directed. Yeah, the first one is a diag.
and second one is not DAG.
Why it is not
It
diag?
it has a cycle. It form a cycle in
Correct.
vertex 2, 3, and 4.
Two. Correct. So you can see that there is a cycle in this graph. So if you are able to find a cycle, you can directly say that this is not a diag. Correct? Yeah.
Yes.
And the second thing, what did I say? You have to calculate the in degree. How do you calculate the in degree? For any graph, let's for example the same plot that we can take it. How will you calculate the in degree? So what's the in degree for 0? So you already know, right? What is in degree and out degree? What is in degree? So basically this is the number of incoming edges of any vertices. And this is what? The number of outgoing edges for many vertices. Now can you calculate the in degree? What's the in degree for 0?
1, sir.
Okay, 1. What is the in degree for 1?
2.
What is the in degree for 2?
0.
For 3?
2.
4 also 2.
Can you calculate the out degree also for all the vertices? What is the out degree for 0?
2. 3. 3 is
Three, sir.
Out degree for 2?
0.
Similarly, you can calculate for 2. You can calculate for 3 also. And you can calculate for 4 also. Right? Okay.
Yes, sir.
Let's come. Yeah. So whenever you have a DAG, you can do the topological sorting, or you can calculate the longest path in the DAG also. Okay. So you should be having that graph should be a directed acyclic. So there should not be any cycle in that. So let's see that how do you calculate the topological sorting. It's basically sequence. How will you write the
Sir,
sequence?
in order
Yeah.
to check that if a graph is a DAG or not, like we have to check that the in degree and out degree should be 0 for at least one vertex, right?
Correct. There should be at least one vertices.
So, sir, out of the two examples which you gave, which one was a DAG? Like the second one wasn't because it had a cycle. Was the
Yeah.
first one a DAG?
Yeah, the first one was a DAZ, because you can see that. And so the first thing that you should be checking in, it should be a directed one and it should not consist of any cycle. Okay, see, even though if there is a cycle, that is like then it's not a DAG. Okay.
Okay, sir.
Yeah. And then even if you'll calculate the in degree, you'll get to know that there must be a in degree, that then only this will be a non-cyclic, like a cyclic, not
Yes.
non-cyclic. So if you are able to get the vertices within degree 0, then only you can think of, whenever you'll think also, you'll see that whenever there is a one vertices within degree 0, then only this can be a non like a cyclic graph, right?
Yes, sir.
Yeah. So let's see that how do you do the topological sorting. How do you write the sequence in such a way that you can think of that the later one is somewhat dependent on the previous one. Okay. So what are the steps to calculate the topological sorting? So there is some 3-4 steps that you should be knowing. So the first step is what? So you have to first compute the in degree of all the vertices in the graph. Okay. What is the second step that you should be doing? So you have to pick the vertex which has 0 in degree. Okay, see, whenever you have a diagonal, whenever you are taking out, if you are taking out the in degree along with the edges with it is attached, then also you'll be getting a DAG only. So this is a DAG, right? And you were having the in degree of 0 as 0. So in degree of 2 as 0. If you are removing 2 along with the edges with it is attached. So if you are removing this 2 plus this also you are removing, and this also if you are removing, then also you'll see that the remaining portions of the graph will also be a DAG only. Okay, so the second step is you have to pick the vertex which has 0 in degree and you can add that in your sequence. So wherever you are writing the sequence, so you can add that vertex in your sequence. And the third step is you have to remove that remove that vertex. I told you, right? You have to remove that vertex. Okay, wherever the integrity was 0, and also you have to remove all the edges, all the edges that are incident with edge I. Okay, and then what you have to do is again you have to update the integrity. Of all the remaining vertices. You have to repeat it. Now repeat the whole thing again. So did you understand the steps? What are we going to do to write the sequence, topological sequence?
Yes, sir.
Yeah.
Yes, sir.
Let's write it. So we already have a graph. Okay, let's write it here. So we have a graph. So what is the first step? So what are you going to do in the first step?
Calculate in degree.
Yeah, calculate in degree. What was the in degree for all the things? You have already calculated. The in degree for 0 was what?
1,
1, then 2,
2,
0, 2,
2, and 2.
2 and
2, 2. So the first step is done. First step is now done. The second step is pick the vertices which has 0 in degree. So we'll take this, correct?
Yes.
Okay. So we are taking this and we have to remove this 2, correct? Along with 2, we have to remove the edges also. This edge also we have removed, and this also we have to remove. Correct? Now what is the third step? You have to again update. So you have to write that. First of all, you have to write somewhere, right? So the vertices, wherever you are writing the topological sequence, so the first thing should be 2, right? And then you have removed 2 along with the incident edges. Now you have to update the value of in degree. So what should be the value of in degree for 1? What
0,
should be the in degree? No, in degree.
2.
2, right? So the number of incoming. So this is 1 and this is the second. What is the in degree for 0?
For
1,
0,
sir.
0.
0, right?
0, 0.
Because there is no edges which is coming to 0. In degree is incoming and outgoing, like out degree is outgoing. Okay, for the 4, what should be the value? 1, and for the
1,
3 it should be 2.
2.
Correct? Now which vertices you have to choose? The vertices which has in degree 0. Correct? So you can choose this one 0, right? And then you can write it here in your topological sequence. After that you have to remove this 0 along with all the incident. Correct? Now you have to update the value of in degree again. What will be the value of in degree now?
For 1, it's 1. For 3, it's 1. And for 4, it's 0.
For 4 it's 0, for 1 it is 1. Which vertices you will be taking next? 4,
4.
correct?
4.
You'll be taking 4. You can write the 4 here in your topological sequence. You'll have to remove 4 along with the incident vertex, incident edges. And now you have to update the value of in degree again. And if you are updating the value of in degree again, what should be the value? 0,
0 and 1.
1. Now you'll be writing here the sequence 3, and then again you'll remove 3 from here, and then the edges. Now you are left with one only, so you'll be writing it one here. So this should be your topological sequence. Is this clear to everyone, or should I repeat it?
Clear, sir.
Clear to everyone, right?
Yes, sir.
Yes, sir.
Okay. Now let's come to the longest path in a DAG. Shall we start that?
Yes, sir.
Now we have to read the longest path in DAG. So I'll write the step first. So you have to do almost the half of the things same as the topological sorting. The other things that you have to calculate, I'll write it here. So the first step is you have to again calculate the in degree for every vertices I. Okay. The second step is, so the other thing what you have to do is, one more thing you have to add it. Initialize the longest path to I equals to 0. So whenever you are starting, you will be writing that longest path to I is equals to 0. And you have to write this for all I that belongs to the vertices. The third step should be, you have to find the vertex U with in degree 0 and remove it from the graph and add that U to the topological sorting and give the longest path to U. And how will you update the value? So you have to update it again for all the vertices. That are two vertex U. And you have to, along with updating the value of in degree, you have to update one more thing. So here you have to update the longest path to I also, with all I that are and how will you update the value of longest path to I? So you'll be updating with one formula, that is longest you'll be writing in this way, the maximum of path to I, comma 1 plus longest path to U. And now you have to repeat it. See, here also you are doing the same thing. You have first calculating the in degree for every vertices, and then the only thing that you are doing is you are updating the other thing also. So along with calculating the in degree, you are initializing the value for each of the vertices as 0. So longest path to each of the vertices is 0 in the first step. And then you are finding the vertices u with in degree 0, and you are removing it from the DAG. Okay, and then you are adding that vertices u to the topological sorting, whatever we were doing earlier for the topological sorting also. And then you are giving the longest path to u. Okay, that thing, the only thing that you are updating here is the longest path. So update the in degree for all, and also that adjacent to u, and update the longest path to I. This is what you are adding it here, and again you are repeating the value. And how you are updating the value of longest path to I? There's basically simple formula: longest path to I you are calculating, and then you are calculating 1 plus longest path to u. Okay, and then you are repeating. With the example, maybe it will be clear to you. So we are taking the same example again. Okay, okay, tell me, what are you going to do it here? So from after reading the first and second step, what are we going to do it here? Can you tell me?
Sir,
Okay,
first of all, calculate
yeah.
1 degree.
Yeah, calculate the in degree first of all. So okay, let me tell you. Okay, so what we can do is we have to update two things here. One is the in degree, and the other is the longest path. I can write it in some short form: longest path. Okay, so initialize the value. So I can write it here. 0 here. I'll write it in degree with yellow color, and I can write it the longest path to I as white. So in degree you are already aware of 0, 2, 1, 2, 2. Longest path I have to initialize as 0, 0. All should be 0. Correct?
Yes, sir.
Yeah. So what is the second step that we have to do? So the first is calculate the in degree. The second we have done the initializing the value. The third is find the vertices u with in degree 0 and remove it from the DAG and add u to the topological sorting. And then we have to update the value of longest path to u. Correct? So which vertices I have to take out first?
2, sir.
2, correct? Yeah. So we have to first take out the 2. You can have a topological sorting where you can write it 2. Correct? What should be the value of longest path to 2?
The 4.
No, see, longest path to 2, if you are starting from 2 itself, because we are starting from 2, right? So if we have been asked longest path to 2 should be 0, right? And earlier also the value is 0. You can see the value as 0 here. 0, 0. That's why we have initialized, because we were not knowing from where we have to start. So that's why it was 0 for all the cases. Correct?
Yes, sir.
Okay. So now you can see that the LPT will be 0, at least for the first case, because we are starting from the 2 itself. Now the second step that we are the other thing that we have to do is we have to update the in degree again. So after removing, first we have to find the vertices u with in degree 0 and remove it from the DAG and add u to the, so we have added u to the topological sorting and give the longest part to the u also. So that we have done. So the most important part here is the update the longest part to I, and I is what? The adjacent. I are the adjacent to u. So what is the what are the vertices that are adjacent to U here? For
0
2,
and
what are
4.
the adjacent? Yeah. So it should be the I should be what? 0 and 4. Correct? Is it correct? Yeah. So I is what? 0 and 4. So you have to update the value of longest path to 0, and then you have to update the value of longest path to 4 also. Correct? So what should be the value for longest path to 0? I told you how you'll be updating. See, the steps are pretty simple. Whatever the DAG has been given to you, first you have to write the in degree, and then the longest path you have to initialize everything with the 0. Now you have to choose where the vertices, you have to choose the vertex with the in degree 0. So you have chosen 2. Okay. Now you can remove the 2 also here. I can remove it here. You can remove 2 from here. Okay, I can remove it from here, but you have to update something. You have to, what you have to update? You have to update the in degree and also update the longest path to the vertices which were adjacent to the 2. Okay, so what was the vertices that was adjacent to 2 was? So 0 and 4. So you have to update the value of LPT of 0 and LPT of 4 along with updating the value of in degree of all other vertices. Okay. So if you are updating the in degree for all the other vertices, what should be the in degree? First of all, you update the in degree. So if you are updating the in degree, and that I'm writing with yellow, I guess. Yeah. So if you are updating the in degree, what should be the value? It should be 0 here. It should be 2 here. It should be 2 here, and it is 1 here. Correct? And now if we have to update the LPT also, if you are updating the LPT for 0, so what should be the value? I told you one formula, that is what? The maximum of longest path to I, comma 1 plus longest path to U. So what should be the value? So the first thing is longest path to I, and the 1 plus longest path to U. So what is U here? What was the U for the our cases? 2, right? See, if you have to update the value, so if you have to update the value longest path to 0, because we already know that you have to write those, you have to update the value of longest path to those vertices which were connected to the earlier vertices 2. So 0 and 4 was connected, right? So you have to update the value of LPT of 0, that will be writing maximum of longest path to I, so that means longest path to 0. So LPT of 0 comma 1 plus longest path to U. What was that? LPT, what was U here? So the U was 2 for your case. So that was 2. So what should be the value? This should be maximum of what? What is LPT of 0? For this case, what was the LPT of 0?
0, sir.
0, correct? So it was 0, comma 1 plus LPT of 2. What was the LPT of 2 for the first case?
So it's
Also
0,
0.
so it will become 1.
Yeah, so that was also 0. So 1 plus 0 is 1. So it will become 1 here, right? So LPT of 0 will become 1. So you have to update the value of this 1, comma. So this should be 1. Now you have to update the LPT of 4 also, right? And what should be the value again? Maximum of LPT of 4, comma 1 plus LPT of 2. And this also should be 1, right? Maximum of 0, comma 1. So this should also be 1. Correct or not?
Yes, sir.
Yes, sir.
Yeah, 1. Now the second step is what you have to do it again.
Choose one of the vertex.
Again, you have to choose the vertices with in degree 0, right?
0. Yeah.
Yes, sir.
So you have updated all the things. You have updated the in degree, and you have updated the LPT also. LPT you have updated for 0 everything. So what was the updated value that you have calculated? You have calculated for 0 it was 1, and for
1.
4 also it is 1, and
1.
for the other two cases it was 0, correct? Right?
Yes. Yes.
Yes, sir.
Yeah, now you have to choose which vertices where the in degree is 0. Where the in degree is 0? 0. Correct? You have to choose 0, right?
Yes.
Yes, sir.
Now if you are choosing 0, so what you have to do? 0 you have to add it in the topological. So one list you are creating, right? 2 comma. So you have to create there 2. So you can write it there. So it was 2 and 0 now. So you have to remove 0 from here, and you have, along with removing 0, what other things that you have to do? You have to check which are the
Change.
vertices that were connected to 0, right? And then you have to update the value of longest path to those vertices also, along with updating the value of in degree, correct? See, in the topological sorting, what you were doing, you were just taking out the in degree where you were just taking out the vertices with in degree 0. Here also you have to do the same thing. You have to take out the vertices where in degree 0, along with, after removing those, you have to check which are the vertices that are connected. And for the connected vertices, you have to update the value of the one thing, that is the longest path to those vertices. That is what you have to do. So only one extra step you have to do it here. That's it, right?
Yes, sir.
Yeah. So now if I'm asking, what will you do now here? You'll remove 0, correct?
Remove 0.
If I'm removing 0 here, so what should be the update? Which all other things that you have to update here?
We have to update 4, 3, and 1.
Yeah. So I
Longest
should be
path.
what? I should be 4, comma
4,
3,
3, comma 1.
1, right?
Yes.
Yeah. So let's start. So if I'm removing, I will remove it. Now update the value. LPT of 4. If I'm updating the LPT of 4, what should be the value here? Maximum of what?
It should be 2.
Yeah,
1,
maximum of
comma 1
2,
plus 1.
right? And again,
Yes.
if you are updating the value
Sir,
of
we are doing 1
L,
plus 1 here because in this case the u was 0, right?
yeah, correct.
Okay, sir.
Now again, if you are updating the value of LPT of 3, what should be the value maximum of what?
1, comma 0, comma 1.
0, comma 1. That is 1.
1.
And if you are updating the LPT of 1, what should be the value?
That is also 0, comma 1. That is 1.
That is also LPT of maximum of 0, comma 1.
Sir, for
That should be
3,
1.
how did
Correct?
we get 1? Can you please explain that?
Okay. So for 3 earlier it was 0, right?
Yes, sir.
So earlier it was 0. So 0, comma 1. And 1, from where you have got 1?
1 plus LPT of U.
Sir,
Yeah,
from the
basically
u,
it's,
the 0.
yeah, correct.
Okay, sir.
One thing we are doing it mistake here. For I guess 0 we have for 1 we have calculated incorrectly. So for LPT of 1, what should be the value maximum of what? Maximum of LPT of 1, comma 1 plus LPT of 0, right? What is the LPT of 0? So for 0 it was 1, right? So it should be LPT of 1 is 0, comma LPT of 1 plus LPT of 1. I guess it should be
Sir,
2.
in 3 also it should be 2.
Yes, sir.
Okay, let's see. Yeah, so let's check it. Maximum of what should be the value?
0, comma 1 plus LPT of 0. That
LPT
is
of
1.
3, comma 1 plus LPT of 0, right? This should also be, this is 0, comma 2. So this should also be 2, right?
Yes, sir. Got it, sir.
Got it, right? And for LPT of 4, it should be maximum of LPT of 4, comma 1 plus LPT of 0. That is also 1 comma 2, and this is 2. So you got the value now. You have updated the value to 2. So now you can update it, right? So if you are updating the value here, so you have to remove something. You have to remove 0 first of all. You have to remove all the edges. Now you have to update the value. So now you have updated the value. So in degree also you have to update, and then you have already updated the LPT. So what was the LPT? I guess 2 for all the other cases, right?
Yes,
Yes,
sir.
sir.
Correct. So you can write it here. So yellow was for updating the value of in degree. What should be the in degree for 4? This is 0,
0,
right? 1 1,
1,
and the updated value of LPT was 2 2 2.
2.
Correct.
Yes, sir.
Now you can write the topological. So till now, what are the topological sorting that we have wrote it? 2 comma 4, 2 comma
2,0.
0 comma 4. And what was the LPT that we have calculated? For 2, what was the value? 0. For 1, what was the value? For 1, it was 1, right? For 0, it was 1. And for
1,
4, what is the value? 2. Correct.
2.
Now, what the next step should be following? Take out which vertices you have to take out where the in degree is 0.
0.
What is that
Means
vertices?
4. 4.
4. Okay, so 4 we have written it here, right? So 4 we will remove it from here. 4 we have removed it, right? And now you have to update the value of LPT for the other cases. What should be the value for 3 and 1? The LPT of, sorry. So okay, what was connected with 4? I forgot. Okay, 3 was only
3.
connected. So for you, the I is what? 3 only. So you have to update the value of LPT of 3 only. So what should be the value? Maximum of LPT of 3 comma 1 plus LPT of
1
4.
plus 4.
So this is what? Maximum of 2 comma 1
2,3.
plus 2,
2,
right?
comma, yeah, 3.
3. 3 should be the value, right? So now we are left with 1 and 3. You can update the value of LPT. What should be the value of LPT now? 3, and this should be 2 only. What is the in degree now? The in degree is 0, and the in
0,
degree is 1. So
1,
which one you have to remove? Now you have to remove 3, right?
3.
So you can write it here, topology, in the topological sorting, whatever we were writing, 2, comma 0, comma 4. Now you can write it 2. What is the longest distance? So LPT for 2 was 0,
0,
and for
1,
0, 1, 2, 3.
2, and 3.
Correct. Now you can remove this one. 3 you can remove it from here, and you can remove this also. And now you can update the value for this. I is 1. You can update the value of LPT of I. You can write it here. Maximum of LPT of 1 comma 1 plus
1, comma 1 plus 4. No,
3.
3,
Yeah,
3.
yeah. So this is basically how much you are getting 2 comma
2, comma
1 plus 3. So
4.
4 should be the value. Correct.
yes.
So this is your topological sorting, and this is LPT. Is this clear to everyone or not?
Clear, sir.
So you'll be able to do it, right?
Sir, can you explain once?
What?
So, sir, in this case, the longest path is 4, right?
Longest path is 4, yeah, and you have to go it. So if you are going from 2 to 1, it will take some. So like the one is the longest path, and the length that you can say is 4.
Okay, sir. So,
Yeah,
so the vertex, like if we are starting from 2, then when we go to vertex 1, it will be the longest path, and we would have to cover 4 vertices, right?
correct.
Okay, sir.
Okay, so you can check it here also if you have what was the plot. So this was our plot, right? So you can check it if you are starting from 2. So to go to the longest path to, what was that? 0. Sorry, 1, right? So what can be the path? To reach 1, what can be the path if you're starting from this one? And then you have this one. So this will be your path, right? The longest path to 1 from 2,
Yes, sir.
right?
Yes, sir.
Hey, who is this man? Please, like, mute yourself. So this is
Yes.
done. I guess whatever we have discussed till now, is it was clear, right, to everyone?
Yes, sir.
Someone wants you to explain it again. In chat box, he has written.
Okay. Okay. So
Sir, you'll be sharing me the PDF of this, like the notes you're writing, right?
I can share it if you'll just this can't be shared on the portal, but okay, if you'll just mail me, I'll just share it. Okay,
Okay, sir.
the file I can share it with you, or anyone who wants this PDF, I can share this PDF. I'll just change it in the PDF form and then I can to you. Okay, so what I was discussing is the longest path. So the procedure is pretty simple. If you are able to understand the topological sorting, then it is pretty simple to understand the longest path also. In the longest path, to calculate the longest path in a DAG. Okay. So basically, I'll start with the DAG again. So basically, a DAG is a graph that is directed, but you don't have any cycle in that. Okay. If you are able to find that, you can say that this is a DAG, and then you can calculate the integrity. After calculating the in degree and out degree, you will see that there is at least one vertices with in degree 0 and out degree also 0. Okay, that will make you confirm that this is a DAG. Okay, to calculate the topological sorting, I told you have basically a simple procedure. You have to calculate the in degree for all the vertices and then check for which vertices the in degree is 0. Wherever the in degree is 0, you have to take out that vertices. You can write it in some list where you are managing, or you're writing the sequence. You have to start with that sequence where the in degree is 0, and then what you have to do is, along with removing that vertices, you have to remove all the edges which were connected, okay, or the incident edges that were connected to that vertices where the in degree was 0. Okay, you have removed that, and then again you have to update the value of in degree. Okay, again updating the value of in degree, you will see that again you are getting at least one vertices where the in degree is 0. Then repeat the procedure. You go to the in degree where the in degree is 0, write it in the topological sequence wherever you were writing, remove the edges that were incident from that vertices, again update the value of in degree, remove the in degree where the where the in degree is 0, write it in the topological sorting. So this is what you have to repeat in the topological sorting. Now come to the longest path. So here you have to update one more thing. So the longest path to the vertices I. So what you have to start with, you have to calculate the in degree again, okay, and then you have to initialize the longest path to I. So you can initialize the value 0. Why? Because you are not knowing that from where you are starting, correct? So you have to start from somewhere. So that's why we initialize with 0 for all the vertices. And now you have to find that vertices where the in degree is 0. Again, repeat the same thing, whatever you were doing in the topological sorting. So basically, you are taking out the vertices where the in degree is 0. Okay, but the one thing is, there you were just updating the in degree again after removing the vertices along with the incident edges. Here you have to update the value of lpt, the longest path to that I also, and that I should be the incident vertices, like from where you can reach from the starting vertices where the in degree was 0. Okay, so you can see that in our example we have started with 0 1 4 2 3. Okay, so we have some 5 vertices. we have updated the value of in degree, and the in degree you can see that for 0 it is 1, for 1 it is 2, for 2 it is 0, and for 3 it is 2, and for 4 it is 2. We have updated the value. We have started, we have initialized the LPT also 0 0 for all the cases. You can see that. And now we have checked out where the in degree is 0. So you can see that for vertices 2 the in degree is 0. Correct. So now we have take out that vertices. We have wrote it in some sequence where we were writing. Okay, so 2 we have written it here. You can see that. And now we have removed 2. So in the second case you can see that we have removed 2 along with the incident vertices. So this we have removed, this also we have removed. So you can see that in the second step we have removed those vertices, but we have, after removing, we have write it in the topological sorting sequence wherever we were writing the topological sequence. And now along with that, the second step was to update the value of in degree. Correct. So we have to update the value of in degree in the second step. So we have updated the value of in degree, but along with updating the value of in degree, we have to update the value of one other thing that we have initialized with 0. Okay, so we have to update the value of LPT, the longest path to I also we have to update. Correct. So for I, so the what is the incident vertices from 2? So 0 and 4 was the incident vertices, 0 and 4. So we have to update the value of this two. We have to update the value of LPT longest path to these vertices only, because from 2 you can reach 0 and 4 only. That's why we are updating for 0 and 4. And what is the updation method? How are we going to update it? The updation method is maximum of LPT of 0, 1 plus LPT of 2. Basically, this is LPT of I, 1 plus LPT of, so you can reach it 0, right? You have to reach it 0 from 2. So what should be the updation value? So LPT of 0, or you reach it from 1 plus LPT of 2. Okay, so this is basically LPT of I, 1 plus LPT of U. U was your vertices with the in degree 0, and I is the incident vertices from the vertices where the in degree was 0. Okay, and then you have to repeat it again and again till the time like you are left with only, you're not left with any vertices. This is what you have to do it here. Is this clear now? Maybe you can just go and solve the same example again, or maybe the other example that will clarify you now.
Yes.
Okay. Okay, so let's start with the other method that we have to go. So the other thing that has been discussed here is the shortest path. Okay, so the shortest path, I'll just discuss the brief about the shortest path with very basic graphs. Okay, and then maybe I guess most of you haven't seen the lecture, that's why I guess I'm not getting any response from anyone. So whatever I'll just discuss the shortest path. So the basic idea I'll give you. Go through the lectures, and then maybe it'll be clear for you guys. Okay. Then after that also you'll meet again. Maybe after that you'll be in the better position to ask the doubts and all.
Sir, can you please explain what a weighted graph is?
Okay. So see the normal. So what is weighted graph? This is pretty. See what happens in a weighted graph is, it's just that in the normal graph you are not given the cost to reach from one place to other places. Okay, in the weighted graph, so some form of, so one can be your cost. Let's for example, you have been given a graph like this is a place. Not I'm writing AB, I can write it like this also. So this is basically Patna, this is Chennai, this can be your Prayagraj or Allahabad you call it. And then this can be Vellore. These are some places. Okay, this is Hyderabad. So this all can be your vertices, and then there is some connection. Okay, so there is some connection. So see, if you have not been given the weight, the thing that you can infer from here is from there is some flight from, so you can reach from Patna to Chennai. Okay, so I haven't given any direction also. I can think of in that way that we can reach it from Patna to Chennai also. There is a flight from Chennai to Patna also, or from Chennai to Allahabad, or from Chennai to Patna and Allahabad. There is some method that you can reach it there. But if you have been given the weighted graph, that means some cost or time or something has been given to you also. Let's, for example, there can be some price also. That so if you are going from Patna to Chennai, let's for example, some 10K you are investing. Okay, from Chennai to Allahabad, you are investing some 15K. Okay, so something has been given. Okay, some X, Y, Z. Okay, A. So this can be your cost. This can be any other thing also, the time also, how much time, so maybe 5, 6, 7, 8, 9. So this can be your time also, that from Patna to Chennai, whatever the flight it is, it takes 5 hours. It won't be, but I'm just saying you. Okay, so this
Yes,
can be, this can represent you the weightage of that. Okay, this is what the weighted graph is. Did you get the idea?
yes, sir.
Yeah. So in the same weighted graph, basically you have been discussed about something. Okay, so you have been discussed about how can you calculate the, so from the single source. So basically there are three methods. I'll just discuss the one today. Okay, so there is like three method that is there. So for the weighted graph, what you have to calculate the shortest path from a single point. Okay, and if you have been asked to calculate the shortest path, because see, if you have been some weighted graph, that means if you have to reach it from Patna to Chennai, there can be a other method also. See, if you have to reach from Patna to Chennai, so there is a direct flight, that is fine, but you can have a flight such a way that there is some place X, you have to go X, and then if you are going to Chennai, here it was taking some 10 hours. Okay, and here it is just taking 2 hours from here and 3 hours. So if somebody is a time constant, so if a person has to reach Chennai quickly, if there is some flight, so direct flight is taking that like more time. It's not possible, but okay, I can just think of some scenario here. And then you have, if you are going via X, then you are taking just 2 to 2 plus 3, so 5 hours only. So it's better to go like this, right, with one halt. Okay, than going direct. Okay, this is what you can think of. So if you have been asked, you have to calculate the shortest path from P to C, then you can say that P to X and then X to C can be your shortest path depending upon the weight, right? If the weight was not given, then you can directly say that it's going better to go from P to C directly. But if some information is given to you, that time or some, if let's for example the direct flight was costing some 20K, and then here it is costing some 5K and then 7K, then also you can think of this. If you are just have to manage the prices and all, also you can think of that going like this, right? This can be your best way to go from P to X and X to C, because it will be a time constant, like the money constant also. So you'll be able to save some 8K here, right? Here also there is some algorithm that will help you to know about the shortest path from a single point, or maybe there is an algorithm that will help you to know the shortest path from any vertices to the other vertices. Okay, so the first thing is the Dijkstra algorithm. In this algorithm, basically you have to calculate the shortest path from a single point. Okay, to some other point in a graph, but the information, the main thing here is there should not be any negative weight. So there should not be any negative values in the weight. Whenever the weight was given, P to C, but maybe this X and all. So there should not be any negative value. This should be a positive value only. Okay, this is what has been given to you. And if so, this algorithm will work there only. If you have to calculate shortest path from a single fixed point, okay, to some other point, and the thing that is given to you is there should not be any negative weight. Okay, that should not be there, right? Then you can use this. Then you can use this algorithm. Okay, the second thing is when you have to calculate the shortest path from one fixed point, right? Here the negative weight is allowed. Negative is allowed. But the problem here is there should not be a negative cycle. Is not allowed. Then you can use this method. Then you can use this Bellman-Ford algo. And the third is you can calculate the shortest path from any vertices to any other vertex here. Also the negative weight is allowed. But negative cycle is not allowed. Okay, then you can use the Lord-Varsel algorithm. Okay, this three method has been given to you to calculate the shortest path. Okay, so the first method is you have to calculate the shortest path from the single point that has been given to you. The second is the shortest path from the single point, but the negative weight has been given, but the negative cycle should not be allowed. What is the negative cycle? Can somebody tell me about the negative cycle? What is negative cycle? So first thing is negative weight. So it can be something like from P to C to X. There can be a negative value, right? Can be something like 20, 10, and then -5. So this is a negative weight. So you have a negative weight in this graph. Hey, are you able to understand, or I'm just speaking out something?
No, sir.
No, sir,
We are
getting it.
understanding.
Getting right? Okay. So this is like negative weight. So they have been given the graph where some of the values are negative, some of the weights are negative. But what about the negative cycle? So negative cycle is such graph where when you are adding it all the negative, all the weight now, it should be negative. That is what negative cycle means. So if you have this P, C, X, so this is like 10, this is 20, and this is minus 40. So if we are adding it up, the negative weighted value, this is coming out to be less than 0. So this you will call it in a negative cycle. Did you understand that?
Yes, sir.
Yes, sir.
Yeah. Okay, so let's discuss the first method. So this is the first algorithm. This is Dijkstra algorithm. So I'll just explain with you some very basic example. This is some P, some what is this P, then this is A, then this is B. Okay, and if you have been given 20, the weight has been given to you. So if you have to start it from here, okay, so what can you do is, see, in the Dijkstra algorithm you just have to, so basically in the this algorithm one thing you have to do it. So whatever the cost for that du has been given to you, plus you have to add the cost for the edges, and if this is less than d of v, then you can update the value of d of v. This is what you have to do it every time. You can think of, so see, and initialize the value with infinite. So you can just initialize all the values with infinite. So if you are starting from p, so this is basically you haven't you can just think of in that way that there is uh, some places p, and then there is one place a and there is one place b. So there's some three places p a b. If a fire has started from point P, or the place P, okay, and then it is going with some speed. So it will, let's for example, it's going with some basic speed it is going. So it will start going in all the path, right? It will go in all directions. So there is one direction this, and there is one direction this one, correct? So it will start going in all the direction, and there will be, and it will go in some same like uniform speed it will go. So basically it takes some 20 second or 20 minutes, you can think of, to reach it a, right? So if you'll just think it from t equals to 0 to t equals to 20, you'll see that at t equals to, see, if you have started with t equals to 0, at t equals to 20 it has reached a, and now from a the fire has started again. So if you'll think of at t equals to 20 now you can think of in that way that at t equals to 20 the fire would have reached somewhere here in this while going from p to a, but it has reached already to a, right. Now if you think of in t equals to 30, then you can think of that the fire from this way would have reached here, but it has already burned the place b, right? So the shortest path to go from p to b would be what? P to a to b, right? So the fire would have reached from b to, if the a, b has been burned, so the fire would have reached from a, right? From p to a to b. So this is what you can think of in this, for the simplest case, the shortest path. So in the Dijkstra algorithm, what you do basically is you starts with that, think of that there is some infinite time that it takes to reach that place. So you can think in that way that you can start with, you are starting with here, but you can think at this as an infinite infinite. This also you can think as a infinite. What did I say? So this is the only thing that you have to check. So you can think of this as a u, and then v as this, right? So what you can see is, what is the cost for, so du is what, you're starting from there itself, so it will be 0. So basically du is 0 plus what is the cost for UV, what is the cost for this? This is 20, right? This is 20. And if this is less than, so this was infinite, right? So this is infinite. If this is less than infinite, you have to update the value. If you are getting, if this is happening, then you have to update the value of dV. And the updated value would be 20. So this you will be updating it here. So you will remove it here, this infinite, and then you'll update the value as 20. Correct? Now again you will be for you, again you can change the du and dv. So now you can think of this du. Now you can think of this as u and u as this as v. And if you are taking it as a du again plus c of dv less than dv or not, then you can think of this as 20 plus 10, right? Is less than infinite. So this is what, again you can update the value of dv equals to 30. So this you can again delete it and update the value as 30. Okay. You can think in that way also, this as u and this as v. So this is what basically du, again you can think of du plus cv less than dv or not, then you can think of this is 0 plus 40. Is it less than 30? No, right? So you will not be updating the value of dv. So dv will be same as 30 because this is not occurring, right? So this is what we were thinking of. If du plus cub is less than dv, then you'll update it. Otherwise, you'll not. So again, you are left in the end. You'll be left with this only, right? So you can think of this to reach it from t to b. You'll be taking some 30 weight, whatever the 30 it is. We are not bothering about that. So this is the shortest path that you can reach. Is this clear to you?
Yes, sir.
Right? This is the simple one, right? Okay. So I'm giving you one example. Can you solve it? You can start it from here.
Right, so what
So
is
for
the
all the dash,
target
for
vertex?
all the, yeah, you have to calculate for all the vertices, for all the destination, from 1 to 2, from 1 to 3, from 1 to 4, 5, 6. Can you
Okay,
give me the
sir.
shortest path? Yeah.
And so there is, so what is the weight for 3 to 6?
Where is that? 3 to 6. Okay, you can take it in anything. You can take it 7. Let's take 7.
Okay, sir.
Or you can think of this as 2. Yeah, now solve this one. So what you can do is, see, you can start with all the infinite value, right? You can start from each destination. So okay, just you can try it and then we'll solve it. If did you get, okay, I'll just try to give you an idea. Or maybe you can just start with one and reach okay, 4, you can reach it. So I can start with 1, right? Okay, did you try that?
Yes,
You
sir.
can
So just a second. The one
okay.
for 7 is. Yes, sir. Done.
Got it right? Okay,
Yes, sir.
I'll solve it. So there is some basic procedure. Okay, so you can start with some source. This is a source. This is the destination. Okay. So what is the source? The first one is the 1. I need to go it till 2, 3, 4, 5, 6. So I told you to start it from infinite. So let's, for example, you take infinite time to reach from 1 to 2 or 1 to 3 or 1 to 4 or 1 to 5 or 1 to 6. Okay. Can I get the direct relation from 1 to 2? Is there any direct relation from 1 to 2? Okay. Can I reach it? So this I can think of the here 0 plus 7 is less than infinite. Correct. So can I write it from 1 to 2? I'll be taking 7, some weight, time, whatever it is. Right. Is there
Yes, sir.
any connection from 1 to 3? 1 to 3, you can think of 0 plus 9 less than infinite. So this is 9 also. So we'll update it to 9. Can I get from 1 to 4? 1 to 4, there is no connection. So I'll put it at infinite only. 1 to 5, can I get from 1 to 5? That is also not possible. So we'll put it at infinite. 1 to 6, we can reach it by 14. So this is 14. So 0 plus 14 is less than infinite, right? So this is 14. Now you can select the the distance you can reach. So to reach to, this is the minimum distance, right? Correct?
Yes, sir.
Yes.
Right? So now you can take out the 2 route. So you can take out 1 and 2. So with the help of now you have to find a way. So 7, you have to update the same thing. You have to update the 7 again and again, right? Because there won't be any uh, path from where you can reach from 1 to 2 in the better way than this, right? Now, while using 1 and 2, can you reach 3 with less than this 9 weight with the help of 1 and 2? So from 1 and 2, you can go this way, but this is what? 7 plus, this is the weight is 7 here. So 7 plus 10, is it less than whatever the 9, the updated value 9?
No,
No,
sir.
right?
No,
So the
sir.
value will be 9 itself, correct? Can you reach 4 with the help of 1 and 2? So you can reach 4 now, right? This way, this and this. So this is 7 plus 15. 15. Is this less than infinite? Yes. So you'll update the value. 7 plus 15 is how much? 22, I guess,
22.
right? Correct. So we'll write it 22. Can you reach it 5 with 1 and 2 with the help of 1 and 2? Now also you can't reach it, so you'll put it infinite. Can you reach 1, 6? Can you reach with the help of 1 and 2? Now also you can't, like you can reach it directly with 14. So now you have to check out which is the minimum value now. So you have take out the 2 already. So now the 3 is the minimum, right? So you can reach out 3. So now you can take out 1, 2, and 3. Correct? So you can reach it from 1 to 3 via some weight 9. That is the minimum weight that you can use it to reach 3. Okay, now you can take out 3 also. Now with the help of 1, 2, 3. So this is done. This is done. Can you reach with 2, 4 with the help of 1, 2, 3? Is there any better way that you can reach it to 4 now with the help of 1, 2, 3?
One and three.
Yeah, you can reach it 1, 3, 4, right?
Yes.
So this is how much? 20, right? So that is better than 22. So you can reach it. So 7 is done, 9 is also done. So it will be 20. Can you reach it to 5 with the help of 1, 3, 2? You can't reach it, right? So this also will be infinity here. Can you reach it 6 with the help of 1, 2, 3? So you can reach it like this, right? So this is how much? This was 9. So 9 plus 2. So 9 plus 2 is less than 14, right? So you'll update the value as 11. Correct? Correct? So now this is the minimum. So 7 is done, 9 is done, 11 is done. Now you can take out 6 also. So 1, 2, 3, 6. So now you can take the help of 1, 2, 3, 6 to reach the remaining 4 and 5. Correct? So can you reach to 4 with the help of 1, 2, 3, 6? In a better way than 20? You can't reach it, right? Are you able to understand this, or should I repeat it again?
No, sir, got it.
Got it, right? Can you reach 4 with less weight than 20 with the help of 1, 2, 3, 6?
No, sir.
You can't reach it, right? So 20 will be as it is. So 7, 9, 20, and then 11. Can you reach to 5 with the help of 1, 2, 3, 6 less than infinite? So I can go right 1,
Yes, sir.
3, 4. I can reach it there, right? So what should be the weight? So I can reach it via this method also. So this should be 9 plus 20.
165
So
will
this
be
is
shortest, sir.
26. Which one?
Sir,
One?
165.
1, 2, 5.
Yeah, 165 will be shortest, right? So this will be 14 plus 9. This is 23, I guess.
Yes, sir.
Is there any other method that you can reach it? I guess 1, 3, 6, 5 would be far better. 9 plus 2 would be 11 plus 9 would be 20, right?
Yes, sir.
So you can reach it with 20. That is 20 less than infinite, so you can reach it here. So now out of this 20, 20, so already you have taken this. You can take out any of the two. So 1, 2, 3, 6, 4. Now with the help of all this 5, this 1, 2, 3, 6, 4, can you reach to 5 with a better way than 20? I guess not.
No, sir.
So this would be the case. So 1, 2, 3, 6, 4, 5. And now you can get the weight also. So the minimum cost to reach from 1 to all the other destination. So did you get the idea how to solve this type of problem?
Yes, sir.
Yes, sir.
Yes, sir. Okay. I guess this is done, right? So yeah, so we are done with this algorithm now. Okay, 1 second. So till now everything is clear, right? So Dijkstra algorithm we have discussed. We have discussed about the topological sorting and then how to calculate the longest path in a DAG. Everything is clear, right, to everyone?
Yes, sir.
Yes.
Yeah. So now we have uh, Bellman-Ford algorithm. And this is also helping us to calculate the minimum, the shortest distance from a single point. Single point, or you can say, or source to the destination where negative weights are present. See, what happens in the Dijkstra algorithm is whenever you have a negative weight, na, see, you are updating these all things, right? But if you are able to get a negative, what do you call, negative weight, then what happens is this algorithm won't work here. This algorithm will not work here because, see, you are updated all the things, but if you are, let's for example, you are writing it this as a minus 10, then you will think of this as a this u plus this du plus cb. Whenever you are updating the value, will always be less than. So if you are updating it as a 30, right, so this will be 0 plus 0 minus 10 will be less than 30, right? So this will be what, minus 10. So even though if you are updating minus 10, again if you are coming here, so 0 minus 10, so every time what will happen is, so this value will again come up as a lesser than the previous one, right? So that's why we don't use this method with the, we don't use this algorithm where the there is a negative weight. So that's why we use this Bellman-Ford, because in Bellman-Ford what we do is, if we have a n vertices or n edges, you have to relax every edges n minus 1 times, so that the weight won't affect us. Okay, so did you get? Okay, maybe with the example I'll discuss that. So in Bellman-Ford what happens is, if you have been, I am giving you one example, I have to reach it from A to B to C. This is 10, this is 5, this is minus 8. So what happens in a this, if I'm using the Dijkstra algorithm, what will happen? I have to start, this is the source. If I'm starting from here, A, B, C is there. So I'm giving it infinite. So what is the best way to reach B? A to B. So I can think of this in the first way, it is a 10, right? And then A to C, you can think as 5. So this is the minimum one,
Yes, sir.
right? So you can take out this AC. Now using AC, can you reach it to B?
Sir,
Yeah.
I have doubt. Actually, this graph is a directed graph. Then how can we means reach to B
You
with
can reach it to
C?
with,
Using C, we are not able to reach to A C B. We can't do that, right?
AC, B, you can't reach it. Yeah.
Because it's a directed graph, right?
Correct. But we are going from A to B, right?
Yeah.
Now tell me, if you have to use it A and C and now reach it to B, can you reach it there?
No.
Yeah.
Still, we can go from A to B. We can't use C to reach B.
So this is fixed, right? If you have to
Yes,
go
sir.
from A to what? A to B, it will take 10, right? And A to C, it was 5. So you are fixing the value, this one. Now you can use AC, correct?
Yes, sir.
If you have to reach it, okay. If I'm removing this direction now, now I'm giving the weight. Now if I'm giving the weight, what was the weight? 8, right? Or 5? Now what will happen?
Then minus 3.
Okay, even though if I'm using, what was the direction? Even though I'm using A to C or this one. Okay, a bit like this. The first thing in the Dijkstra algorithm, what we used to do is, we'll put at all the point it will be infinite, right? So from A to this is infinite. So we have put it to infinite. So from source to destination. Now what will happen is, from A to B, what is the minimum cost? That is the 10, right? So we can write it 10. From A to C, the minimum cost was 5 in the starting point. So you can reach it from DU to 0 plus 5 less than infinite. So we have put it 5 here, and here also similarly we have written it 10 here, correct? Now we have now we can see that we have to take out one which is minimum. So out of 10 and 5, the 5 is the minimum, so we have taken out here. So now you can use A and C. So with the help, now you can use it A and C, right? With the help of A and C, you can't reach it to B, correct?
Yes, sir.
Yes, sir.
You can't reach it, right? So but the, yeah, so the 10 will be fixed and 5 will be fixed, correct?
Yes, sir.
So now you can take out ACB. So now you can see that with the help of AC, now you can use ACB anything, right? So now if you see that if you are reaching it to B, you can reach it with 2 only, right? Correct or not? See, in Dijkstra algorithm, what you are doing is you are fixing the value. So after 5, you are fixed to A to C. This is fixed 5 unit, and now you know that you can't reach it to B via C, because AC was like relaxed, right? In the first step, AC was relaxed, so you can reach it to B using AC because you can't use it C. So you can go it from A to B with 10 unit, right? But now if you'll see that while relaxing A, B, C, all three, you can see that you can reach it to A to C via this, right? This was 10. So 10 minus 2 is less than, what was the value of C5, right? 5, correct? So this is, sorry, 10 minus 8. So this is 2 is less than 5. So you have to update the value to 2. But this was not getting updated in this the previous algorithm, right?
Yes, sir.
Okay, so that's why this method was not working for the negative weight. So should I repeat this again?
Yes, sir. Yes, please.
What?
Okay. See, this is A, this is B, this is C. So what I was saying is whenever you have a negative weight, this algorithm won't work. So the method that we have worked on, Dijkstra algorithm, that won't work for the negative cases. And you can see that why. This is 5, this is 8 minus 8. So in this algorithm, what you were doing, we were starting with the source and we have initialized that it will take infinite unit to reach B and infinite unit to reach C from A. So we were doing something. So we started with the source and destination. What was our source is we started with A. You have to reach it destination by B or C. So initial point was from infinite, correct? Now the next method is you have to calculate the distance. So to reach it from A to B, you can think of this as this was infinite. So 0 plus 10 is less than infinite. So we can write it 10 here. Now you can see that from 0, this is 0, 0 plus 5 is less than infinite. So you can write it 5 here. Now one thing you have to relax. So you can fix the value 5. So reach it from A to C, you can fix the value as 5. So this is what we are doing as algorithm. So after fixing the value as 5, you can think of this as you can reach it from A to C with 5 unit, right? Is there any better way to reach it to B from using AC only? So if you are using only AC, you can't reach it to B with less than 10 because you have to go directly from A to B. So this was also fixed. So now, so the algorithm that you have used, that was saying that you can reach it from A to B with 10. This is a minimum one, and A to C 5. This is the minimum one. Now, after relaxing all the three vertices A, C, B, now you can think of, now again go to that graph and now again think of that. So we have updated the value of minimum cost, and that was 10 for this and 5 for this. Now you can think of, while using all the three vertices, you have to reach it to C. So if you are using B, can you reach it 10 minus 8? So this is du for u and this is C u comma v. Now you can think of du plus cv. This was 10 minus 8 and this you are getting less than 5. So if whenever you have to get the less than 5, you have to update the value. So here you are getting 2, but from our algorithm, what was the value we were getting from A to C? This is 5, right? But here we are getting 2. So this is a contradictory, right? So that's why we don't use this method for the negative weights. So that's why we use Bellman-Ford method. Did you get the idea?
Okay, sir. When the values are negative, we don't use Dijkstra.
Yeah, Dijkstra, you don't have to use it. You have to use the other method. And I have written it here clearly. So which method you have to use it? You can get it. So most probably you won't be getting it to cal. So you can get the minimum. See, spanning tree and all you'll be able to get. So this method, so you can given it in the form of statements. Okay. So whatever it's been written here should be known to you. Excuse me. Okay. Excuse me. Sorry. Yeah. Is this clear to everyone? So whatever we
Yes,
have
sir.
discussed, this is clear to everyone, right? So whichever algorithm we have discussed today, it's clear to everyone. Excuse me, sorry.
Yes, sir.
Okay, so I'll stop it here itself. Okay, I'm not. I don't know what happens. So I can send this PDF to whoever. Like I can just upload it on some Google Drive and update it here also. Or you can just mail me. I'll just send the PDF, right?
Sir, there is one query.
Yeah.
In my portal, week 9 open sessions that are available in week 9 is not visible. Other weeks session are solve with us session are available, sir.
Okay, I guess this won't be available for anyone. Maybe you can watch it on YouTube. There will be, so you can go through that. Yeah, but I'll check with the portal team why it's not coming. And there was a mistake, I guess, in one question in the quiz that will also be resolved. I guess some people have sent me that query. I just went through that, and it was I guess we have to do something on that, so we'll do that. Okay, rest everything is fine. So okay,
Sir,
so just go through the lectures again. Week 11. So I have discussed most of the portion. You have been left with only the two algorithm, and I guess the tree minimum spanning tree. Those are pretty simple. You just have to go through the lectures. So just go through that lecture, and whenever you are having a doubt, you can just ask me. Most of the portion we have discussed it today. Okay, so basic what, see, the basics things you should be having clear with the graph theory. The what is minimum vertex cover and what is the complete graph. These all things, if you are clear, I don't think so there is any thing that will not be able to solve the paper. I have been through the paper. Those are pretty direct questions from the graph theory, so you'll be able to solve. Just go and solve all the questions. You'll be able to do it in the exam. Okay. Okay. Yeah. So whatever the doubt you have, you can just mail me, WhatsApp me, whatever you want to do it, you can do it. Okay.
Thank you.
Yeah. Thanks everyone for coming up in the.
Thank you.
Thank you, sir.
And thank you everyone.
Thank you, sir.
Bye, sir. Thank you, sir.
Yeah. Thank you. Thanks.